is happening here. The ring in our case is not going to be unital. So it is true an approach to the theorem is by studying an object which is called the Hecke algebra of the group G. The Hecke algebra of G. I will explain now the definition of this object. This is a, let me cheat first. In order to cheat easily, let me assume that G is compact. Let's consider all functions on the group, from the group to the complex numbers. And let's assume that, OK, so this is a vector space. OK. I'll use this blackboard. You see, we have a mechanism now which cleans things. This smooth operation. Smoothing functor somehow. So it's not really surprising that if I take G, an L group, and I consider now fun G, just f from G to C, f whatever you want. OK? Then I can consider, this is a vector space. And obviously, G acts on this by translation. So this is a representation belonging to this bad category rep G. But I can apply this process. So what I will get from it are functions which are locally constant. It's easy to see. So if you apply the process of smoothing, what we get is something which is sometimes denoted C infinity G, sometimes by other notations, but it doesn't matter. Let's use that. So these are functions f from G to C, so that f is locally constant. OK? Now, I'm not saying that the Hecke algebra is this vector space, because this is just a vector space with a G action. I don't know how to multiply elements there, or maybe I know, but that's not what I want. It turns out that I can try, given two functions here, to convolve them. OK? So what we want is to have a convolution. And this raises two technical issues. Technical issue number one, convolution requires integration. Integration requires a measure. OK, you say, don't cry. G is locally compact. Locally compact groups do have Haar measure. Take one of those. OK, take a Haar measure. So this is a choice. If you look at your algebraic side, you feel bad. OK, so you don't want to choose. OK, but let's choose. So you choose a measure, you know how to convolve. But you convolve and you get infinity because, well, the integral goes over G, and G may not be compact. I failed to write that G is compact. I said it, but I didn't write it. So if G is compact, then I would be able to do that. OK, so we can solve this issue by considering a sub-vector space, C infinity Cg. So these are functions on G which are locally constant and have compact support. This is the candidate. Essentially, this is our Hecke algebra. OK? It's locally constant of compact support. And then a theorem which I would say predates this result, or at least in the logical development, it would come before declaring that the category is an abelian category, would be the following. Let me erase there. So I said that we want to have some approach. So at the moment, there is a missing link. I never said that h of g is equal to c infinity cg. I just said it's almost the same. Just to be honest, this would just be the space of locally constant measures of compact support. Okay, so that's the only thing you have to say. And then the theorem, is the Green Party doing well? Not so good? No, it's okay. I'm just asking whether green is admissible. So the theorem is that the algebra HG is almost unital. This is not a mathematical notion. The mathematical notion is called even worse. It's called idempotented. Idempotented. And the category of non-degenerate modules over Hg, denoted M of Hg, thanks a lot, is equivalent to Mg. And additional study of the category of non-degenerate modules over idempotented algebras in general allows one to show that they admit the properties written above. Okay? So I will write down in a second the definitions, but this is the formal setup in which we embed the concept of representations of L group into modules over a certain algebra. Okay, so I think I just looked at the clock. Maybe it's a good time to do a 10 minute or 5 minute? How does it work here? Whatever. Thank you, Dima. Okay, so so maybe now it's the time to say a little bit about idempotented algebras and non-degenerate modules, and I will just say a little bit about that. So the definition. So let me first draw you a picture in your mind, and then I will write down the definition. So the picture is this. The algebra Hg, and for that matter, an idempotented algebra, should be, in some way, be a union of unital algebras. So what would happen if you would take some kind of limit of unital algebras? That's some picture to think about. Then you also want to have a relationship between these algebras. Let's say one is contained in the other, but, or maybe there is a map between these algebras, but not necessarily requesting that a unit of one algebra goes to a unit to the other. So that's a general picture or situation that we are going to have. So in order to beef it up, let me just write down an example here. In some sense, okay, we have seen a lot of examples. For every L group, the algebra Hg is an example of. But before, I feel better with having some example before writing down the formal definition. So basic example. So if we consider functions on GL2 of QP to the complex numbers, and we assume that they have compact support. And that they are smooth. So remember what smooth means. Smooth means that this function, which secretly is a vector in the space of all functions, is a smooth vector. Namely, it is stabilized by some open neighborhood of the identity. Just a second, how the function can be stabilized? Who is acting on it? So our very group, GL2, is acting on it by translation. So the condition of smoothness turns out to be that our function, in fact, is invariant from the left, but because of this compact support also from the right, with respect to a small neighborhood of 1. Namely, one of the groups Km, which was exactly on this blackboard. So the smoothness condition can be rephrased as follows. There exists an integer m so that for every k1 and k2 in km, the congruent subgroup, which I'm going to remind you by writing it in a symbolic way, 1 plus p to the m, p to the m, p to the m, 1 plus p to the m. Okay? This is the group of 2 by 2 invertible matrices. When you reduce them mod p to the m, you get the identity matrix. Okay? So for every two guys here, f k1 g k2 should be equal to f of g for every g in GL2 QP. So we can think about our function f as follows. It has compact support, and it's smooth of, let's say, level m. Elements which are really small, very close to 1, do not alter my function. OK, so let's think of an example of something like that. So any example? One such function? Yes, the 0 function. OK, let's proceed. Indicator function of some neighborhood of identity. For example, the indicator function of this very group Km. OK? So this is the notion of a function which has compact support, and it is smooth. OK? So if we fix the smoothness, namely, if we consider the collection which is denoted sometimes by HGKM, so this is this collection when I erase this thing. OK, so I put in bracket the quantifier, the existential quantifier, and insist that my functions here have compact support and exactly have this Km smoothness, then the claim is that this is a unital algebra with respect to convolution, the unit element being our friend, the characteristic function of this subgroup Km. This is the unit element of this algebra. What? You are absolutely right, but OK, I'm on this level of exactness. OK, so now, OK, but that's not the end of the story. We don't care about HGKM. We care about HG. What I'm telling you is that HG is a glorified union of these algebras. HG, so exercise, HG is a union of HGKM over M. OK? So it is in this respect that this algebra is not a unital algebra. If you increase M, the subgroup Km becomes smaller. There is a relationship. If you are invariant with respect to K7, you are invariant with respect to K17. On the other hand, the unit elements of these two algebras are not the same. OK? So this is the structure that we have. So formalizing it is the following. So let me see what kind of yes, so I will make some assumption, which may not be necessary, but I will make it. So let A be an algebra over C. I want to define the notion of idempotented algebra. It's a general notion which will include in particular this algebra H of G. Yes?
Maybe that's what Sasha asked, but the unit element is the characteristic function up to some scala, right? Up to some normalization.
Yes, yes. Let A be an algebra over C, assumed to have countable dimension. Okay? We say that A is idempotented if there exists a collection, I will assume it's a sequence, yes, EI of elements of A such that. So naturally, these EIs, the letter E comes because these are idempotents. So E squared is equal to E. Okay, so again, in your mental picture, you should view these elements, characteristic elements of Km, as this idempotent. This is the EI. EM is this guy. So 1, EI are idempotents. Okay? So x squared is equal to x. Okay? And the second condition is, in some sense, means that A is non-degenerate over itself. So I will formulate it as follow. For every A in A, EIA is equal A times EI for I large enough. So for every particular element in your algebra, if you go down further enough in the stream, you get an identity behavior. Okay? So this is the definition. And I owe you another definition, the definition of non-degenerate module. So for such algebras, it is natural to consider modules M such that A times M is equal to M. What does this mean? On the level of elements, it means that for every element in M, you can find an element of A which act on it as if it would be the identity. Okay? It is for this reason that I said that this condition is, in some sense, making this algebra over itself. Okay, so this is the condition. And the notation I retain, M of A is the category, relevant category, of non-degenerate A modules. Let me put it upstairs. Is it visible? No, it's not visible. I'll write it again. Just a second. What? Remove the markers seems to not be that helpful, but no, just have to be more careful with writing. So M of A is the category of non-degenerate modules. So theorem A is that let G be an L group countable at infinity. So this means that G can be covered by a union, countable union of compact subsets. This is just the standard definition of countable at infinity from topology. Then H of G is an idempotented algebra, and the category MG is equivalent, whatever that means, to the category of non-degenerate modules over H of G.
Countable at infinity means sigma compact?
Yes. Okay, so okay. There is now a chapter in algebra, it's not a big chapter, of how to study modules over idempotented algebras by studying them over unital algebras. The basic idea is that if you want to study modules over an algebra like that A, it turns out that, okay, so it's not so clear how to study all modules, but you can study irreducible modules. So irreducible modules you can study by reducing the problem to a unital algebra. So maybe I'll just give very sketchy discussion of this idea, but again, before it was a mistake to erase this, but okay, so in some sense, you can hold two pictures in your brain. One of them is the interaction between G representations and HG modules. And another is that you have non-degenerate modules over some algebra A, which is idempotented, and some modules over a unital algebra, an auxiliary unital algebra, which I will denote by B. So let me explain what is going on. So these two pictures are not the same, but they are related. Okay? So in some sense, they are in a chain. The following is happening. Think about GL2, for example. So suppose I have a representation of GL2. Every vector in my vector space is smooth. So it is fixed by some compact open subgroup. Okay, it is fixed say by K7. Okay, so I can let the Hecke algebra associated with K7 act on my representation. So given V a representation of G, I see that H of G acts on V, okay. In fact, I can see shreds of these action on subspaces of V. Namely, let me continue this analogy here. In some sense, these are two equivalent theories. You can talk in this language or talk in that language. I'm just trying to message the basic idea. On V up, so let K in G be open compact. Then HGK is a unital algebra, open, compact subgroup. A unital algebra, and now it's a key observation. Consider, it's a key trivial observation. Consider the subspace which is denoted by V upper K. It is the space of vectors in V which are fixed by the subgroup K. Here, the letter pi denotes my representation. So in the background, I have fixed a representation of G. This is fixed. And I can play the following game. Why should I have only one vector space when I can create zillions of that? For every K, I can look at V upper K. It's all the vectors which are fixed by this K. Now, this is a vector space which might be smaller. Okay? On the other hand, it admits an action of this algebra. So the key observation is that HGK acts on VK. Namely, if a vector is fixed by K, I can act on it by a function from this Hecke algebra. The action is obtained by certain integration, and the outcome is also in VK. So I have traded one representation to many, many representations of unital algebras. So a similar maneuver one can do in the realm of idempotent algebras by doing that for every idempotent. So the game here is being played by, so if E is an idempotent of the algebra A, one can consider the algebra B to be EAE. This is the algebra that one studies. It's a unital algebra. And the process which is called reduction to a unital algebra, which I just now called it like that, is allowing you studying modules over A on which the element E acts non-trivially as modules over B. Okay? So the more formal result, let me write it down, and probably I will settle with that. I've written to myself something which might be relevant. So let us observe that P is an A module. It's a left module. And we can define two functors. We shall define the following objects. So B, it's better to define it not by just saying it's EAE, but rather in the more intricate way, saying that it's the endomorphism of this P, which of course is EAE. The two functors I'm alluding to are the following. The first is the following functor. It starts with modules over A, and it yields, maybe I'll write down the formula first. The functor would be just the home functor by P. So home PM. So this defines the map.
All the home
Defines.
The home and ends are over A, right?
Yes. Defines. So this is a map. A module over A. It's a non-degenerate module over A. And this home. So this is maybe not so evident. At first, this home is just maybe a C vector space. But in fact, there is an asymmetry here. The endomorphism of P acts on this variable. So this is, in fact, a module over B. So this gives a functor from modules over the algebra A to modules over the algebra B, which is, as I said, a unital algebra. As I said, this process is not so much different than this one. This V uppercase is this thing, okay? Just it's a more abstract way. On the other hand, we can also create, so maybe an exercise to construct a functor in the other direction. So you know who is adjoint to home, yeah? You heard about it. It's your friend, the tensor product, okay? So let me just give names. So I'll call this functor R. This is the functor I. So I of a module N will just be an extension by P of this thing. Okay, so because P is an A module, this admits a structure of an A module. And so just check that these two functors are adjoint. This is left adjoint to R. And now maybe the key reduction, which is hidden in this construction, is the following. Consider, so E is an idempotent of A, and we will consider two sets, here E of A. So you can guess what this is. This would just be modules over A such that E does not kill them. So these would be irreducible modules which are not killed by E. And consider here B. They are in a bijection. Okay? So this is some kind of an exercise about this idempotent algebras, just to get a feeling. Okay. I think enough about that. This is a direction which allows you to study representations of the group using modules over non-unital algebras. What I want to focus now is on some basic questions that one asks in the representation theory as an algebraist. And these basic questions are the usual things, namely Schur's lemma or the like. So I would call this level 0 representation theory of p-adic groups. Namely, these are the basic things which you want to achieve, just to know that the basic things are true. So what are the basic hopes when you think about representations of groups? The first thing is that irreducible representations of abelian groups would be one-dimensional. So let me leave all these things to you as an exercise. Let me just make a list of exercises which are worth thinking about, not necessarily trivial. Okay? So I'm just making a list of things which are not going to be a great surprise, but we still want to know them. So G an abelian L group, V an irreducible representation, then V is one-dimensional. Okay? Do we have enough information in order to prove this? I leave this to you, but I may answer tomorrow if you if people will be interested. The second is G, a compact L group. V, an irreducible representation. Then V is finite dimensional.
Here you always talk about smooth representations.
Yes, yes. I only talk about smooth representations. Yes. Okay. Another natural question, which will turns out to be less trivial but still correct. G, a compact L group. V, a representation of G. Then V is completely reducible. So let me remind what complete reducibility is all about. So again, there are a few basic facts from representation theory in a very general setup. Complete reducibility is one of the most important things when you study representations of finite groups or compact groups in standard theories. And it may or may not comes as a surprise that it plays also an important role in the theory of representations of p-adic groups, although it totally fails. Although it totally fails, it's a key in our understanding of the representation theory because we somehow squeeze and do our best in order to study our representations through compact subgroups. Okay, so we will see that later. So complete reducibility have, so this of course means either V is a direct sum of some irreducibles, or for every W in V G invariant, there exists a W perp G invariant, which is a complement. So it's an exercise to show that these two things are equivalent. Okay? And maybe it's a challenge to prove that for a compact group we have complete reducibility. Okay? Namely that every representation of a compact group is completely reducible. Okay, so every smooth, yes, I'm talking about smooth representations. Okay, so these are a class of things we want to know, but here is another class of, so these are generalities, and I leave you as a challenge to try to study these things for one afternoon. Yes?
Reducibles are the smallest object in this category. Can't we have something like indecomposables? Like something which is...
Yes, why not? Yes.
Would that be...
But so in principle, we are interested. So we are interested in irreducible representations. I'm not sure I understood your question, but we can always define notion of indecomposability in principle because so you see, the point is that when you have complete reducibility, then these two things are coinciding. In all other cases, I don't see a way to say something intelligent. Okay? Okay, but now let me say something intelligent, or slightly intelligent, about other type of generalities. So second type of, so these are kind of list of wishful thinking, of which are all correct. Second wish list comes from, which will be important. It comes from two directions. The first one is Schur's lemma, and the second is something which is called sometimes separation lemma. Let me elaborate about these two things. So these are generalities which are very relevant when you are trying to understand representations. So what is Schur's lemma all about? You are given a representation V. So there is the basic of the basic Schur's lemma. You have V and W G representations, and they are irreducible. Then what do you know about this home? So you know that if this home is non-zero, I'm just giving you the most trivial of all Schur's lemma. Suppose you have a morphism between V and W, two G representations, which turn out to be irreducible. Okay, so let's analyze. T is a map from V to W. We can consider the kernel of T. It's a subspace of V. If V is irreducible, then this leaves us two possibilities. Either the kernel is everything, in which case T is the zero map. Okay, if we assume that this home space is non-zero, we can choose T which is non-zero. Okay? Zero is always there, but if we take T which is non-zero, it implies that the kernel of T has to be zero. And its image has to be everything. This is because of irreducibility. So it follows that T is an isomorphism. So this means the following. Irreducible representations are very lonely, categorically speaking. At least if you only look at the skeleton of irreducible objects. Irreducible can talk only with itself. It cannot talk with anyone else. Oh, sorry. Two irreducibles can talk only when they are the same. So the really interesting Schur's lemma is about discussion of a representation with itself. Okay? So let me write what we just said. Schur's lemma, take 0, home, VWG non-zero, VW irreducible, implies V isomorphic to W. Okay? Fortunately or unfortunately, this is one of the strongest tools we have. This stupid observation. Okay? Schur's lemma really is V irreducible representation, then okay? So this is a criterion to see if a representation is not irreducible. If its endomorphism is too big, then it's not irreducible. Now, in some sense, if it would be decomposable, if a representation is a sum of two irreducibles, then obviously the endomorphism would not be C. But the key here is that this is for irreducible. Okay? So let me discuss the proof. It's not trivial. Proof is not trivial. It's not deep, but it's a bit tricky. Let me discuss that. So I call this generalities from algebra. So generality. So the proof is based on the following two generalities. So actually, to be honest, the proofs, I didn't talk about the separation lemma, but let me immediately write down these two generalities. And so I talked a little bit, I did talk about Schur's lemma. Okay, take 0 is obvious, take 1 we are now proving. Okay, so let H, so I'm now forgetting about G and working about over some algebra. be a C algebra, I will not assume it's unital for the second, of countable dimension. Okay? So I remind that when G is an L group of our type, the Hecke algebra is such an algebra. Okay? So the lemma is just this thing. Let M be an irreducible H module. So an irreducible H module means that it does not have a non-zero sub-H module. No proper sub-module. Then the endomorphism is C. So what I'm telling you here is that no groups are relevant. This is not a statement about groups or about p-adic groups. It's a statement about algebras. Okay? It's a totally general statement. And in this form, it can be relevant for problems in the realm of universal enveloping algebras. Okay? So when one studies representations of Lie groups, of Lie algebras. I think in this form, it's sometimes attributed to Dixmuir. Anyway, let me give the proof. The proof has two steps. Step one, or maybe three steps. Step one, let me denote by A the endomorphism of M. By what we have just seen in the language of groups, this is a skew field. Namely, every element here is invertible. Maybe it's not commutative, but it's a skew field. Okay? Step two, A has countable dimension. This is very easy. I leave you as an exercise to think about it. One uses the irreducibility for this. Okay? I remind that H is assumed to be countable dimension, so M, it follows that M is also countable dimension, but you have to say something further. And the third step is a famous fact, again, I don't know due to whom, that if A is a skew field of countable dimension over the complex numbers, so it's a vector space over C algebra, then A is equal to C. I shall give the proof of step 3 because it is beautiful, not because you don't know it. Just I do it because I enjoy it. Okay, so proof of step 3. Okay, so with this, the end of the proof is given. This gives the proof. Okay. Okay, so we are given an element A in A, and we want to show that it belongs to the complex numbers, so that it's a multiple of the identity element of A. So we want to show there exists a lambda in C such that A is lambda times 1. Okay? That's what we want to prove. So how to do that? We consider, otherwise, we consider the elements A minus lambda times 1, where lambda belongs to the complex numbers. And this set is uncountable, so it has to be linearly dependent. After all these elements belong to A. So this means that we can find Ci and lambda I so that this is equal to 0 for some value of k. Ci are not all 0. So if we clear up the denominators, we get a polynomial q which is non-zero, so that q of a is equal to 0. We just multiply by the product of these guys. Okay, that's it, we are done. Because q factors, so q of x is a product of x minus mu I goes from 1 to n, whatever. Times a constant, thank you very much, which is non-zero. And on the other hand, if I substitute a here, I get 0. So this is a contradiction because all these guys are invertible. It's impossible to multiply invertible guys and to get 0. Okay? It's a skew field. If you want, I can argue positively. This is equal to 0, so it means that at least one of them is equal to 0. And this is a contradiction. Okay, so just a nice proof. I decided that. Okay, so a similar proof, just a similar proof. Repeat this proof, and you can prove something which I called here separation lemma. And let me write it down. But now we will have to assume that our algebra is unital. So the lemma is the following. Suppose that H is unital. And let A in H be a non-nilpotent element. So just an element that no power of it is equal to 0. Then the statement of the lemma is that the following important fact. There exists an irreducible H module M. You don't have to ask if it's non-degenerate. H is unital, yes? Such that if I consider A as a map from M to N, well, just A from M to M is non-zero. This means that you can save every element of the algebra. Every element of the algebra which is non-nilpotent is visible on some module. Okay, this is called separation lemma. So the proof should at the moment be an exercise for you. But I will give you a few hints. I will just write you 2 or 3 steps for the proof. So step 1 is to prove the following. There exists a non-zero element in the complex numbers such that A minus lambda is not invertible. Let me write this in a more intelligent way. A not nilpotent implies the spectrum of A is not contained just in 0.
Would you not require H to be countable dimension?
I do all the time.
Oh, okay. Also
Yes, yes. I do all the time. I think I wrote it before the lemma. Okay, yes, it doesn't matter. Your question is it's a good question. That's what I'm assuming. In fact, I believe that one can actually, okay, I don't want to say this on record, but at least for the purpose of the study of representation of locally compact groups, this particular proof of separation lemma can be replaced with a more functional analysis proof. So using the the Krein-Milman theorem, one can show such a result in a much more general setup. So this assumption is needed just for this particular proof. Okay, so step one is to show that for some lambda a minus lambda is not invertible. This is the same. This is essentially repeating this proof. Step two is to consider the module just a very simple one. I take H itself. H is a module over, is it H or A? Yes. H, and I divide it by the ideal generated by my guy, by A minus lambda. So this is a non-trivial module. And it's, of course, it's finitely generated by one element, just by the one here. Okay, maybe I'll write here H. Okay, I didn't talk about that, but that's not a difficult fact to show that if you have a finitely generated module, then it has an irreducible quotient. Okay, so more formally, take the maximal submodule of n, which does not contain the image of 1. Then this is n0. N mod n0 would work. Okay, so essentially this gives the proof of the separation lemma. I have to finish soon, so let me just give you a heads up on what I want to do tomorrow, what I wanted to do today. I wanted to do to talk about a notion which is called a compact representation. So it turns out that instead of working with compact groups and proving complete reducibility for compact groups, it is more useful or more relevant to study a general notion, a notion which exists for every group, every L group, notion which is called compact representation. Actually, to be honest, most L groups do not even have one such a representation. But up to the center, all L groups will have compact mod center representations, and this would be the beginning of connecting some kind of analysis to algebra, because we will have a basic theorem by Harishchandra which translates the notion of compact mod center representations and cuspidal representations. So this would be the beginning of the tour to split the category. Okay, thank you very much for your patience today.